Calorimetry is a process that we use to identify the heat given off by various samples. This is used quite often in food laboratories to determine the amount of calories in food products. Calorimetry depends on the law of conservation of energy. The law of conservation of energy tells us that energy can neither be created nor destroyed. So all of the energy that we start with, we must also end up with. As it applies to calorimetry, a lot of times we look at it as the heat lost by the system. Remember, the system is the chemical reaction or phase change that you are studying, must be equal to the heat gained by the surroundings. And most often in a calorimetry problem, the surroundings is going to be the water in which the chemical reaction is occurring. So to calculate this, we have a formula. So we can say the heat of the water, remember Q stands for heat, representing our surroundings, is equal to negative the Q of your sample or your system. Make sure that you include that negative, okay? If you don't include the negative, then your answers are usually going to be incorrect. So it's Q equals negative Q. Let's take a look at a couple of calorimeters. So the one on the left here, this is a very primitive calorimeter, something like we would use in the classroom. It's just made out of coffee cups for insulation. And so all we're going to do in a calorimeter, whether it's this primitive one or this more fancy one, is you're going to have a heated up sample, whatever that sample is. You're going to take the temperature of the water before you put the sample in and after you put the sample in. And from that, we can calculate how much heat the water absorbed. And from that, how much heat was lost by that sample. Let's take a look at a couple of examples. Our first example says a 77.5 gram sample of an unknown solid is heated to 62.5 degrees Celsius and placed in a calorimeter containing 93 grams of water at 23.3 degrees Celsius. If the final temperature of the mixture is 26.2 degrees Celsius, what is the specific heat of the solid? Okay, so a couple of key things that tell us that this is a calorimetry problem versus just a regular heat calculation. First of all, they do use the word calorimeter. That's going to be a very good keyword for us. But if they did not give us the word calorimeter, we could tell that this is a calorimetry problem because they gave us information about two things. They gave us information about our unknown solid, our sample, and they gave us information about the water. And so that's also a big hint that this is going to be a calorimetry problem. So our formula for a calorimetry problem was the heat of your system or your water, or whichever one you want to put on the side, does not matter, is equal to negative the heat of the other thing. So in this case, I have the heat of the solid equal to negative heat of the water. Well, if we go back to our question here, they didn't give us any values for heat. So this particular formula is not going to be very helpful to us. However, in the last lesson, we learned three formulas that we can use to solve for heat. And one of those formulas we used for temperature changes, which was MC delta T. So I'm going to replace those Q's with MC delta T. So on this side, I'm going to have the MC delta T of the solid, and on this side, MC delta T of the water. Okay, so now we can plug everything in. So looking at, again, just the solid, the mass of my solid was 77.5 grams. We don't know what it is. That's what we're looking for. So we're going to have our C for specific heat. That's going to be our X, or we can leave it as a C. Then we do our delta T. Remember, final minus initial. The final temperature of the mixture was 26.2. The initial temperature of the solid was 62.5. That's all the information that we have about the solid. Then we'll bring down our negative. Don't forget the negative. Now we're going to put all the information that we have about the water. So we know that the mass of the water was 93 grams. We can look up on our answers or our reference table that the specific heat is 4.18 for water. And then again, delta T, final temperature was 26.2. Initial temperature of the water was 23.3. Okay, solving that out for our C here, we get that the specific heat of our solid was 0.401 joules per gram degrees Celsius. Okay, let's do one more. So this one says a 50.6 gram sample of iron metal is heated and put into 104 grams of water at 19.7 degrees Celsius in a calorimeter. If the final temperature of the iron and the water is 24.3 degrees Celsius, what was the initial temperature of the iron? Now, the chemistry on this one's going to be just as simple as the one before, just plugging in all the information that we have. But the algebra and the way that we have to solve for our x this time is going to be a little bit more difficult. Okay, so because it's a calorimetry problem, we start with our Q equals negative Q. In this case, I'm going to put the iron on the left, the water on the right. Again, it does not matter as long as you're consistent with your numbers. Again, we can't use Q because they did not give us any values for Q. So we're going to replace that Q with MC delta T. All right, so since we're doing iron on the left, we have a 50.6 gram piece of iron. We can look on our reference table to find the specific heat of iron, which is 0.449. We know that the final temperature of both of them was 24.3. And in this case, we are looking for that initial temperature. So that's going to be our X, or I'm just going to leave it as Ti. Bringing down the negative, on the water side, we had 104 grams of water. Our reference table tells us that the specific heat for water is 4.18. And then again, final minus initial, the final temperature of the water is 24.3. The initial temperature of the water was 19.7. Okay, so this time we have to solve for our variable right here. So the first thing I'm going to do is I'm going to do everything on this side. And so I get negative 1999.712. And I'm going to multiply these two things together to get 22.7194. Now there's a couple ways that you can proceed from here. I'm actually going to distribute this number through those parentheses. And so when I do that, I do 22.7194 times 24.3, which is 552.08. And then 22.7194 times negative Ti gives us minus 22.7194 Ti. And then that we just brought that down. Okay, so then we will add this over and subtract that over, and to get everything on the same side. And then solving for Ti, we get 112 degrees Celsius as our initial temperature.